Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the latest episode of the podcast we like to call Space Nuts, because we're nutty about space, the space between our ears. And joining me as always is Fred Watson from the Australian Astronomical Observatory. Hello, Fred.
Hi, Andrew. That would be empty space, wouldn't it?
It's dark matter. That's what it is.
Dark matter,
dark matter in there. Or grey matter, whatever turns you on. Now, you're in your office, I see. I've never seen your office. What are all those things on the shelf at the back?
Those things on the shelf are books.
Never seen them before.
Yeah, that's all right. Well, welcome to my office at the the Anglo-Australian Telescope. I think I have actually recorded a podcast here with you before, but we might have just done it over the phone, Andrew.
Yeah, maybe.
So that's why it feels like an unusual event.
I'm just trying to read all on the spines, written by Fred Watson, written by Fred Watson, written by Fred Watson.
I don't even know. Oh, yeah.
You know you're supposed to let other people buy them.
Well, that's because nobody did.
Oh, we're in the same boat. Yeah. Very good. All right, today, Fred, we're going to look at multiverse theory. We've talked about multiple universes before, and there seems to be a groundswell of belief that this is possible until today. Now they've decided, oh, hang on a sec, we've found evidence to suggest that they may not be real. So we'll have to look into that, and we'll have it all solved by the end of today. We're also going to look at now. I got a question about this earlier in the week, and we did send an answer in, but there's more to it than this. And I'd say this is what's prompted the question. We didn't realise it at the time, but NASA looks like sending a helicopter to the Red Planet. The question was, will it work? And that's a good question. And we're going to look into the possibilities of putting a helicopter on Mars and how it might be made to work. It's a very different world up there. And a question about EM drives, electromagnetic drives. And I have a suspicion that I know where this question came from as well. So we'll look into that. But multiverse theory, Fred, it's certainly something you and I have discussed before. And there does seem to be some kind of belief that there might be multiple universes, not just the one we're in, but now there seems to be a series of papers that suggest otherwise, or may suggest otherwise. They're not saying no, but they're saying less likely.
Well, the reason why they're saying less likely is because one of the motivations for postulating multiple universes has certainly not disappeared, but it's reduced. So let's go back in history, probably 20 or 30 years, when it was sort of first noticed. And in fact, it was the Astronomer Royal, Professor Sir Martin Rees, who noticed this because he wrote a book about it. It was noticed that the fundamental properties of the universe, things like the speed of light, the charge on the electron, and other fundamental things like that, seem to be very, very well tuned. So if you were sitting in a room with all these things in knobs, and you could control, all the different properties of the universe, it looks as though somebody twiddled all the knobs to make the values exactly such that the universe would expand, that it would form stars, that it would form planets and galaxies, and eventually humans, so that there would be an intellect there to understand the universe. In other words, these fundamental properties seem to be very finely tuned towards life originating.
Right.
That's the bottom line. So if you twist the knobs one way or the other, or tweak them slightly, then either you get a universe that expands too rapidly and tears itself apart very quickly, or you get a universe that doesn't expand rapidly enough and just collapses on itself within the first 2 weeks rather than lasting 13.8 billion years.
Sounds like my driving test. But anyway, carry on.
I hope that didn't go for 13.8 billion years.
It
might have
like
felt like it to the examiner, yeah. So so we've always appreciated that these fundamental constants are very finely tuned, and what that has, well, the first thing that you would say about that is, gosh, isn't that amazing that if these things were any different, we wouldn't be here. But then the second thing you think of is why should they be so finely tuned so that they exactly fit the requirements needed to evolve life? And the suggestion that was made, indeed by Martin Rees and others, was that perhaps what we've got is a whole multitude of different universes with different fundamental parameters, different speeds of light, different charges on the electron, different dark energies, which is where we're going to get to in this discussion. What if you had all those, a multiverse, and it just happens that the only one that can spawn life is the one that we're in, and that's this kind of replicating argument in a sense, self-promoting argument, because you've said, well, the universe is here. The one universe that we have is here because we are here. In a sense, it's putting us very much as part of the equation when you're talking about these tweaks. So, cut to the story today, which is about dark energy. So one of the fundamental parameters is this really mysterious thing we call dark energy. It's discovered 20 years ago, very recently, certainly in terms of the history of astronomy, by a group led by, well, two groups actually, one led by an American, one led by an Australian, whose name is the team. It's hard to identify one person, but the person leading the team was Professor Brian Schmidt, now the Vice Chancellor of the Australian National University. So Brian's team were one of two that worked out that the universe, rather than slowing down in its expansion, as we would have expected 13.8 billion years after the Big Bang itself, rather than doing that, it's actually expanding more rapidly. And in fact, it seems to have been expanding since it got to half its present age. It seems to have been accelerating in its expansion. And that is now attributed to something we call dark energy. Dark energy is thought to be an energy of space itself, rather than something in space. It's space itself that has this energy. And so the bigger the universe gets, the more of it there is, because it's proportional to the volume of the universe. And so the universe expands ever more rapidly. Now, the problem with dark energy is we haven't the faintest idea what it is. And the best theoretical models that the physicists can come up with, these are people who build models of reality inside computers, the best models they get suggest, they're out by a factor of trillions. Their models say that dark energy should be much more energetic than it is, and actually the universe would not exist if that was the case. So dark energy is much less than the theoretical predictions suggest. And until now, we've always thought that it was finely tuned to this idea of life forming. But the new research, which comes from a project called EAGLE. Let me see if I can find out what EAGLE stands for. Yes, EAGLE is the Evolution and Assembly of Galaxies and Their Environments. So
makes
it's a great
sense.
acronym. Yeah, it makes
Good
sense.
one, that one.
So what the EAGLE team have done, and they're led in the UK, the University of Durham, but there are people at Sydney University who are working on this. They have built models of how galaxies should behave quite nearby, relatively nearby, out to a distance of about 300 million light years. Sounds like a long way, and it certainly would be if you were walking. But in the scale of the universe, it's fairly nearby. So they've built models of 10,000 galaxies within this volume and looked at the way those models behave when they change the fundamental parameters. And in particular, they've changed dark energy. And then they've compared it with Hubble telescope data for the same volume of space. So what you've got is a theoretical model, which you can tinker around with, and also a set of observations of what reality looks like. And what you're trying to do is find out how well matched the model is to reality, particularly when you start tweaking the numbers. and their results have been surprising because they've discovered that you can actually change the amount of dark energy by a couple of hundred times, and you still get the same kind of universe. You get the universe that we have in reality. And that suggests that maybe dark energy is not so critical in terms of exactly what setting it has. It's not so critical to the origins of stars, planets, galaxies, and life as we thought it was. And that maybe maybe that's a bit of a furphy, that you've got to have exactly the right amount of dark energy in order to create life. Now, this is only about one parameter. It doesn't cover things like, the others I've mentioned, charge on the electron, speed of light, all those other things, mass of the proton, these really fundamental things. So they, for the time being at least, look as though they are pretty well set for life, and that still speaks on behalf of a multiverse, or the idea of a multiverse. But dark energy has kind of relinquished its grip a bit on the idea that maybe there are millions of universes out there and not just one. So it's a tiny step in furthering our understanding of whether or not there might be a multiverse. And, you said at the beginning of this segment that we might have an answer at the end of it, and the answer is still, it depends.
Yes, and I figured that was going to be the answer. However, they could be absolutely wrong because, as you said, we don't know what dark energy is, so we don't know what impact it really is having to the nth degree. We've got a bit of an idea of what it might be doing. So they might be off the mark to a certain degree in terms of its wider influence.
Yeah, exactly.
I'm not saying they're wrong, because they're much more intelligent than me and they've done a lot more work to figure it out. I mean, I stay up at night trying to figure it out myself, but I just have this sort of inkling that we're delving into a realm of absolute unknowns, and you can't sort of draw a line under anything yet.
As it has been said before, there are known unknowns and there are unknown unknowns.
Yes.
And at the moment, we're pretty near the unknown unknowns. So you're absolutely right, Andrew. The topic that we're discussing now, when we're making a hash of it, not because both of us have got empty space between our ears, but because
we don't want to sound Durham.
Oh, yes, that's right. A nice one. It's because we're right at the cutting edge of research. These are things that physicists grapple with, in terms of advancing our knowledge. We really do not know the answers to these things.
It's fringe science, isn't it, really?
It's science at the leading edge. And, the reason for discussing it is as much to show where science is going and how people are thinking about these things, rather than to present hard and fast results. Because certainly as far as the multiverse is concerned, and to some extent dark energy as well, there aren't any hard and fast results. We don't know if the multiverse exists, and we don't know we don't know what dark energy is comprised of. But we're working on it, and I think some of this research is very exciting. It would be really interesting to see where we've got to on this topic within a year. I think the bottom line from our discussion now is not to write off the multiverse yet, because it could still be very much the truth of the matter.
We will wait with interest and we will see. Of course, if we ultimately prove that they do or don't exist, it won't really matter, because we can't go there anyway. If they do exist. And if they don't exist, we can't go there anyway. But yeah, it will be interesting to get more information on this if we can. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity. Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
3, 2, 1.
Space nuts.
Next up, Fred, we're going to look into the plan by NASA to send a helicopter to Mars. And as they do write in their official documentation, they're not going to fly it from Earth to Mars. They're going to fly it to Mars and then it's going to take off. Flying a helicopter to Mars would be impossible. But the question has come up from somebody, and forgive me, I've lost your name, but I know you're listening and I know you want the answer to this question, which we sort of gave you a rudimentary response to. But can a helicopter actually successfully fly on Mars, given the fact that it's a much, much thinner atmosphere and much lower gravity? And that is the ultimate question. That's actually why they're doing this, isn't it, Fred?
It's partly that's right, to see whether it's possible. And certainly the technology that's going into it is based on known aerodynamics and known pressures on Mars and things of that sort. So the odds are that this will actually work. The basis of the story is that there is a spacecraft, a NASA spacecraft going to Mars in 2020. I've actually seen it, or I've seen the current state of it, or current as of last year, because I visited JPL, the Jet Propulsion Laboratory in Pasadena, California, and what's called the bus, the framework of this spacecraft, was sitting on the floor of the large assembly bay there, which was great to see. So this is the Mars rover due to take off from Earth 2020 and be a sort of next generation version of Curiosity, because Curiosity is the current rover on Mars. Actually, the previous generation is still operating. That's Opportunity. That's still going strong. Curiosity also going strong after, nearly 6 years now since Curiosity landed.
That's outstanding.
It is extraordinary.
I think once it's all over Red Rover and we've had a chance to look back, people will say that was one of the greatest things we ever did.
I think so too. And of course, what it's shown is that Mars was once habitable. It's shown all kinds of interesting geology, and there is still a lot going on. But the thinking behind this is, okay, if you've got a rover on Mars, what you really need to do is to be able to get a kind of macro scale survey of the terrain around you. You need to see what's over the next ridge. You need to see what's behind that boulder. And if you've got just one vantage point, even though you can move it as a rover can, you still need to be able to, suss out the terrain around you. And a helicopter, a robotic helicopter, just like a drone that we're all getting so used to seeing in our skies here on Earth, that would be perfectly acceptable as a way of scrutinizing the terrain that's just beyond your reach, and that lets you feed much more up-to-date information into the rover itself, so it chooses its path more carefully. It knows where it wants to go because there's a really interesting rock just behind that ridge there. So it's a great idea if you can do it. But of course, the problem with helicopters on Mars, you've got two things, one working in your favor and one not. The thing that works in your favor is that Mars's gravity is about 1/3 the gravity on the Earth. And so that helps you. It means that your 1.8 kilogram helicopter, which is actually what's being proposed, has much less weight on Mars than it does on the Earth. It's got the same mass, but it doesn't. It has a different weight. So that works in your favour. But what works against you is that the air pressure on Mars is only about 100th of what it is here on Earth. And of course, it is the interaction between the helicopter's rotor blades and the atmosphere that makes it fly. And if you've got much less air, you've got a lot harder job to do.
So that would mean, as far as I've researched, you would need a much higher revolution engine to get the speed of the rotors that you'd need to lift. And I imagine you'd need bigger rotors.
That's right. Yeah. So the rotor blades are there are kind of limits to the size of them. Well, let me put it this way: if you want to lift this thing off, you've got to have rotors that are, and by this thing I mean the sort of normal drone-sized entity that is envisaged for this. But it weighs 1.8 kilograms. So that's, or its mass is 1.8 kilograms. So you've got to have something pretty beefy to lift it up. And to do that, you're talking about rotor speeds in the region of 3,000 revolutions per minute.
Wow.
So that is, infinitely faster than what the drones.
That's like dentist drill speed.
It's turbine speed almost. So a drone on Earth, I'm guessing here, but my feeling is that they are they're working round about that as about a tenth or a third of that, something like that. So 600 revolutions per minute would be 100 times a second. And that's probably pretty fast for a terrestrial one. So we're talking about speeds of that sort of order. Sorry, my calculations in my head went awry there. That is much less than a half or a tenth of 3,000 RPM. But you can all ignore that. And we're talking about, the bottom line is we're talking about speeds which are much, much higher. Maybe 5 times higher, something of that sort. So. That then, going back to your question about how big they are, that limits what the size is, because the faster you turn a set of rotors like that, the faster the tips are traveling through the air. And then you get interesting things happening, like the wingtips or the rotor tips breaking the sound barrier on your planet. And that then puts up extra resistance. And it's nice to avoid that if you can. It's one of the things that makes that gives helicopters their standard chug sound as they go through the air, which is when the ends of the rotor blades are breaking the sound barrier. So you get that characteristic thumping noise. Now, all this is going to take place on the planet Mars. So you need to be very careful about how you do it. You can't try it out and then say, oh, that doesn't work. We'll just tweak it slightly and send it up again. It's kind of one-off experiment.
Yeah.
But wait, there's more, because there is another thing that actually makes life very difficult for any kind of Marscopter, as it's being called, and that is that Mars is several light minutes away from the Earth, and maybe sometimes
control it from Earth.
More than half an hour travel time away from Earth. So there's absolutely no way that you can sit on Earth with a joystick and look at a TV screen and say, this is where we want to go, this is how we want to fly, and this is what we want to do on Mars. The thing has to be completely autonomous. It has to be able to look after itself. It has to be able to take off, land, interact with its surroundings, find the bit of terrain it's looking for. It's got to do all that on its own.
Charge its own batteries.
Yeah. Find a charger to plug it in. That would no doubt be carried by the rover, which will have solar panels. But yeah, it's got to be pretty clever. So this is really quite a challenge. It's not anywhere near as easy as people might think, but it is something that I think we will see happening when Mars rover flies in 2020. They're estimating that the helicopter will not really travel much higher than about 3 or 4 meters, that it will stay within a few hundred meters of the rover itself, and basically do its thing completely under its own control. So quite a challenge.
Yes, indeed. But fascinating as well. And if they succeed, well, it will open the way for a new form of exploration of Mars going forward, I would think. It would have to.
That's absolutely right. I think the plans also include an onboard charger, which uses solar power, so that if it does have to land somewhere that's inconvenient and can't get back to the mothership, as it were, then it can charge its batteries up over a period of time.
Okay, so we will know in a couple of years' time where we're at with the Mars helicopter, but we certainly hope it's a success. But just lately, they've certainly kicked some goals on Mars, or hit some home runs, or whatever analogy you want to use. But they've made some big strides forward on the red planet. You're listening to Space Nuts. Andrew Dunkley and Fred Watson, of course.
0G, and I feel fine.
Space Nuts.
Last but not least, Fred, we have an audience question. This one comes from Andy Michaels, or Andy Michel, or Mickles. I'm going to give every possibility so I can get the pronunciation right, because I've got it wrong in the past. Anyway, Andy, thank you for your question. Hi, guys. Love your show. I have a question about the EM drive and why it doesn't get more attention or excitement about the possibilities for space travel once outside Earth's gravity. I get that it's not well understood and seems to defy the laws of physics, but if it works, why not invest in its development? Now, I suspect, Fred, this question may have come about as a result of a science fiction series that I've seen on Netflix, where they're trying to save Earth from an asteroid. And the way they're going to do it is to get to the asteroid and divert it. And the only way to get there fast enough is with a device driven by an EM pulse, which is a system of self-replicating power and self-achieved multiple acceleration, so that it can reach tens of thousands of kilometres an hour. So it'll make the trip in no time, basically. Of course, that might not be where this question came from, but I just think it's a coincidence that there's a sci-fi show that talks about EM drives at the moment. Is there any work developing this kind of technology?
There is work going on it, absolutely. If the drive that we're talking about is something that's sometimes called a radio frequency resonant cavity thruster, then there is work going on it, but it is so controversial that, as far as I know, no big-time players in this game are investing in it. But you can bet your life that DARPA will be looking at it, and DARPA is the Defense Agency's research wing in the United States. They do all kinds of really interesting research, which we sometimes hear about and sometimes don't. What is it? So it's basically, the idea is that you've got something that looks like a tin can, a conical. Well, all right. Imagine a bucket, a metal bucket, with no top and no bottom, and you set up an electromagnetic oscillation inside it, and the proponents of this drive say that actually generates a thrust. You pour microwaves into it, and you get an unbalanced force coming out of the two open ends. So you get a large force coming out the big end and a small force coming out the small end, and those two forces add together. One's negative because it's in the other direction to the first one, and you get a net thrust that lets you push an object forward. So there has been quite a lot of work that's been described on this, but all of which seems to be pretty inconclusive. There has been some work done by NASA. There's a team which is known as the Advanced Propulsion Physics Laboratory, sometimes called EagleWorks, which doesn't really make an acronym, but never mind, which is devoted to the idea is that they look after exotic concept for propelling spacecraft. And they've tested all kinds of things that you might describe as fringe proposals, and I think this is one of them. I don't know to what extent their work has been successful. They have published papers, but given that nobody has yet leapt on this and said this is the way of the future, I suspect that there are still doubts about whether it actually works, and part of the reason is it's very difficult to test. You've got to test it under experimental conditions, which means probably in weightlessness and in a vacuum. So it does mean you need to take one of these things up in space and actually try it out. I think there are plans for the Chinese government to test one of these things on its on its space station, but I think if you took a gang of 100 scientists and said, okay, who backs the EM drive, it would not be that many, and more scientists would be looking at the ion propulsion drive, which is another what was once thought to be exotic, where you've got an inert gas like xenon or something like that, and you feed it through. You basically turn it into a plasma and accelerate it out of a jet nozzle. So you're using solar power, the electricity generated by sunlight, to turn this gas into a plasma and blast it out the back of your rocket, but you're not burning anything. Now that's a conventional rocket in a sense, because it's taking something and firing it out the back, and the change in momentum is what lets you move forward. It's very different from the so-called EM drive, which seems to be something that does not require an exchange of momentum, and that's why so many physicists struggle with it, because it seems to defy the laws of physics, and we don't really understand that, if indeed it does work. So I think there is work going on this. I think it'll be work that perhaps within the next year or two will come up with a conclusive answer as to whether this is a real potential solution to rocket, to spacecraft design. But then you've got to find a way of generating the huge amounts of power that you need to make it work, because that is one of these things that does not come for free. You've got to get power into it.
And then you've got to control it. And if it's capable of the sorts of things that we're hearing about, then control is another factor that needs to be solved. And it also prompts a question in my mind, something we've talked about before, but not for a long time, of the same ilk as the scramjet. That's got a bit quiet, hasn't it?
The supersonic combustion ramjet, as it's called, the scramjet. Look, there is work going on. I know that University of Queensland is still very active in this field, and I think there are aerodynamicists at the University of Sydney who are also working on it. So once again, it's something that's work in progress. Clearly, rocket motors turn out in the end to be rocket science. It's pretty hard to do it right and to get things that will work, especially these exotic, what you might call fringe designs like the EM drive.
Yeah, I think the problem is that they need to power it with dark energy, and they don't know what dark energy is, and until they figure it out, they can't make it work.
Quite so.
That might be the problem. Yeah. All right. So, yes, there is work on this, Andy, but we don't think it's all that serious in the central core of the astronomical world at this stage, or the scientific world. But sometime, Fred's going to come up with something that's going to solve our distance problems in space. I just think that there's an unknown technology ready to be, unravelled sometime down the track.
And you are the person to unravel it.
Yeah, I might just tie myself up in knots, more likely. But I just think that we were achieving things now that people 100 years ago would never have envisaged, and we use technology today, and to a certain degree, we still don't know how some of it works, even a mobile phone or a cell phone, if you want to use the American vernacular. But I think the time will come. I just do.
The big breakthrough. Meanwhile, don't just tie yourself up in knots. Tie yourself up in nuts.
Yes,
Space nuts.
Space nuts. Good one. Yeah. Thank you, Fred. And thank you to your air conditioning mechanics who've been a part of the show today. If you wondered what all those bumps and grinds and noises were in the background, it wasn't Fred's brain. It was an air conditioning fit out. Thank you, Fred. Was, yeah. Thank you as always.
No worries, Andrew. Good to talk to you again, and we'll speak again soon.
We will indeed. Fred Watson from the Australian Astronomical Observatory. And thank you for your company this week, and join us again next week. Don't forget to get in touch via our Facebook page or whatever medium you use to communicate. And we will look forward to talking with you again next week on Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.